Let's dive right into this. Welcome to The Explainer. Today, we're unpacking a really fascinating mystery sitting right at the bleeding edge of artificial intelligence. We're going to look at why aligning AI, getting it to actually do what we want it to do, has become such a massive, tangled web. And this is especially true when we're talking about large language models.
To really get to the bottom of this mystery, we have to start with a fundamental question. Why do AI alignment failures look so remarkably different in language models compared to other systems? Look, alignment issues aren't exactly new, right? AI has always struggled with things like reward hacking or just completely missing the intended goal in robotics or game playing. But those older failures were usually just technical glitches, kind of only legible to specialists in a lab. But Today, large language models fail so fluently, so visibly, and honestly so publicly. So we gotta ask, why?
Well, the failures we're seeing right now are incredibly specific to the medium they operate in. We're seeing specification gaming, where the AI basically cheats the rules to win, but it's rendered in perfectly fluent, beautiful prose. We see models confidently hallucinating completely non-factual content. There's sycophancy, where the model acts like a total yes man, arguing really persuasively for its own flawed outputs just to keep the user happy. And of course, jailbreaks, achieved not by hacking code but through really clever linguistic reframing. These aren't just your standard math errors, they are fundamental failures of interpretation. Which brings us to Section 1, Text, a unique domain. To solve this mystery, we really have to point the finger at our primary suspect, the medium of text itself. Independent researcher Joshua Duran proposes a brilliant structural theory to explain all this. His conjecture is that natural language discourse is the, and I quote, canonical partially structured domain. In plain English, he's arguing that these failures look the way they do because of the deep structural nature of text itself. The AI didn't invent these alignment problems out of nowhere. It just made them highly visible because it's operating in literally the only domain that constantly reports on itself. Duran identifies 4 unique properties that create this chaotic environment. First, there's local compressibility. Basically, grammar and idioms are highly predictable, which gives AI models a really great initial grip on the language. Second is global underclosure, meaning is literally never final. It entirely depends on context and how things are framed. Third, we have hard multi-scale structure. Just because you master letters doesn't mean you master sentences, and mastering sentences sure doesn't mean you grasp global themes. And finally, the wild card, reflexive self-description. Text can actually describe, revise, and even argue about other text. When you put all 4 of these together, they create an unmatched, wildly tangled ecosystem. Now, to scientifically test if this ecosystem can actually be untangled, researchers needed to isolate just one of these properties. They zeroed in on that 4th one, focusing on a variable called reflexive metadiscourse. Basically, this is language through which a text refers to, organizes, or qualifies its own discourse. Think of everyday phrases like, as noted above, or to clarify. The whole goal here was to see if we could somehow separate texts that use this feature from texts that don't, without messing up anything else in the process. Moving right into Section 2, the balance transfer phenomenon. Think of stage 1 of their experiment as the very first attempt to pull just this single variable out of a massive corpus of natural web text. The researchers took 5,000 text pairs, one with high reflexive metadiscourse and one with absolutely zero, and tried to match them up on all the other controls so they could compare them cleanly. First, they tried what's called penalty matching. This perfectly balanced continuous controls like passage length and compression, but it completely failed to balance the underlying semantic meaning or the topic clusters. So they pivoted. They tried exact cluster matching to essentially force the semantic meaning to match exactly, but doing that immediately threw the compression, the length, and the recurrent structure totally out of whack. And this brilliantly illustrates what the researchers dubbed the balance transfer phenomenon. Honestly, it's exactly like squeezing a balloon. You force all the air out of one side by perfectly matching up that semantic meaning, and suddenly the imbalance just bulges out the other side, messing up your passage length and compression. You literally cannot cleanly isolate a single property. The researchers summed this up perfectly, noting the location of the binding imbalance changed across matching regimes rather than disappearing. It turns out natural text fundamentally resists being neatly taken apart. The properties are just too structurally entangled. Let's transition over to Section 3, the intervention illusion. So the researchers thought, okay, if you can't find naturally matching text to compare, you have to make them. But to run a genuinely rigorous experiment, you can't just delete a phrase like to clarify and say, hey, look, the text changed. You have to prove beyond a doubt that the act of editing itself didn't cause the change. It's exactly like a medical trial. You need a sham edit, a linguistic placebo. If you delete 5 words for your true edit, you gotta delete 5 non-reflexive words for your sham edit to introduce the exact same level of textual disturbance. Only then can you make a fair comparison. To keep the science airtight, they set up a strict validity firewall. Before they were even allowed to look at the scientific outcomes, like how the edits actually affected the AI's alignment properties, these edits had to pass automated machine validity gates for meaning, fluency, and that sham control matching. But the experiment hit an absolute brick wall. It failed right there at the machine level. Human adjudication and the actual scientific endpoints were never even authorized to begin. The results here were really striking. The insertion operator, where they basically tried to artificially inject reflexive markers into the text, completely failed to preserve meaning, fluency, and length. It only passed about 79 to 84% of the time. As it turns out, you can't just forcefully shove a phrase like, in other words, into a paragraph without totally breaking the local discourse flow. Let's move on and see how this builds, because this failure created massive sample attrition. They started with 2,000 attempted pairs for both deletion and insertion. But by the time they filtered out all the broken edits, the insertion arm had only 879 machine-eligible samples left. It fell way, way below the minimum floor required to even run the experiment. So what we end up with is this highly asymmetric failure profile. Deleting the target words actually worked technically, sure, but creating the placebo sham controls for that deletion failed miserably. On the flip side, inserting words successfully changed the target density, but it bluntly failed to preserve the core integrity of the text's meaning and fluency. Now, what's really interesting about this is exactly why those deletion placebo controls failed. The researchers decomposed the causes, and the token word counts matched perfectly. If they deleted 5 words, the sham deleted 5 words. But when you break down the data, the massive disparity is obvious. The composite syntactic disturbance, specifically the punctuation repair, was a complete mismatch. The researchers concluded with this incredibly powerful insight. A linguistic control can match an intervention exactly in token burden and still fail to match the disturbance introduced by that intervention. In other words, deleting a non-reflexive phrase requires entirely different punctuation and grammatical repairs than deleting a reflexive phrase. The whole surrounding structure reacts completely differently. Which brings us to our final part, Section 4, Why Language Resists Control. So the crucial point is that this brings our whole detective arc to a close. We now see exactly why our suspect, the medium of text itself, is so guilty. Text operates as this highly tangled, deeply interdependent ecosystem. Meaning is always deferred, it is entirely context-dependent. You can master one scale, like local token prediction, but that mastery doesn't cleanly transfer over to another scale, like overall thematic coherence, and reflexive feedback loops just accelerate these problems. Ultimately, fixing AI alignment in language models isn't just an engineering problem of writing better code. It's wrestling with a fundamental structural property of human language itself. Surgical edits will inevitably disturb the whole environment. Which leaves us with a profound question to end on. If human language fundamentally resists being mathematically isolated and cleanly controlled, what does this mean for the future of building truly aligned and safe AI? Are we just trying to solve a structural impossibility with more computing power? It's certainly something to think about. Thank you so much for joining me for this explainer, and keep exploring.